Recent thing I mentioned is are there any other groups of order 4 possibly? And it might have sounded like an impenetrable question for someone. Uh, how do I find another group? How would I know if there's another group? You've only given me these ZNs and these UNs and these tiny little building blocks, and I can't just make up groups out of anything, but that's exactly what we need to do in order to answer this question. You see, we already know that there's this group of groups, collection of groups, which are all the same and have two elements which are their own inverses, exactly two. And there's this other group of groups which have all four elements are their own inverse, right? So we have those with two elements and four elements. And we've shown that the ones with two elements are all the same. We saw, because we made an arbitrary one where two elements are their own inverse, and we saw it was the same as the others that have two elements their own inverse. And we did the same with ones where everything is its own inverse. So what are the other possibilities? There's only four elements. So could we have a group with one element, which is its own inverse and nothing else? And could we have a group where three of the elements are their own inverse and nothing else? Those are the only other possibilities, because we've seen that all the ones that have the two elements of their own inverse and four of their own inverse, all of those are going to give us the same table. That assumption alone is enough to generate the table. So let's try to think about this. Suppose you have three elements which are their own inverse. It's a group, so every element has to have an inverse. So if, say, E, A, and B are their own inverse, what's going to be the inverse of the next element? What's going to be the inverse of C? It can't be E, it can't be A, and it can't be B. So C would also have to be its own inverse. Now, slight objection. You might say, well, what if E is the inverse of E, and A is the inverse of A, and B is the inverse of B, but B is also the inverse of C? Ha ha. Well, it turns out that inverses are unique. That is, B and C. What do I mean by that? I mean, you can't be the inverse of two different elements. Suppose we have some X inverse, and that's equal to Y inverse. So we have some elements X and Y, and they have the same inverse. Okay, well, what could I do in this situation? Well, I know that X inverse equals Y inverse, they're the same, so I could multiply by X on both sides. And this will cancel and give me the identity, whatever that identity is. But I could also multiply on both sides by Y. And of course, because of associativity, by the way, that parentheses is like there, kind of sloppy. Because of associativity, I get this. Okay? What do I have on the left? Well, that's the identity. What do I have on the right? Lo and behold, what do I see? I see that they were the same to begin with. So if X and Y have the same inverse, then they were the same element before we started. You can't have X inverse equal to Y inverse without X being equal to Y. So if you look over here, if we have E as its own inverse, A as its own inverse, and B as its own inverse, there's nowhere for C to get an inverse, because C can't share an inverse with B unless C is equal to B. So that answers that question. We can't have three, no group with three elements of their own inverse. Exactly three, obviously, if the fourth one is its own inverse as well. Okay, so you might say, wait a second, this is okay. We know that two elements are their own inverse and the four elements are their own inverses. cases, and we know we can't have 3. What about a group where there's just one element that's its own inverse? And the element would have to be the identity, because we know that the identity times itself is the identity. So the identity, could we have a group where the identity is the only element that's its own inverse? Could E be the only element that is its own inverse? Okay, well, what would that mean? Well, I know that if A is the inverse of B, that would imply B is the inverse of A, because that would both imply that AB equals E and BA equals E. So if B brings A to the identity, A brings B to the identity. So let's say that E is the only element that's its own inverse, and we have 2 other elements, A and B, which are their inverses of each other. We're in trouble again. There's nothing for C. C would have to be its own inverse, and if C is its own inverse, we're in the Z4 case again. So what have we shown? We've shown rigorous mathematical proof. There are only 2 groups of order 4 up to isomorphism. There are many groups of order 4 in the sense that these groups pop up all over the place, whether you're doing addition and multiplication and eventually maybe moving things around, rotating, but not yet. But we've already seen these same 2 groups come up again and again and again. But all of the groups of order 4 must be either, this is what we've shown, all groups of order 4, they're isomorphic, means that we can reorder or relabel to either Z4 or V, the Klein 4 group. V is the letter we use for the Klein 4 group. So that answers that question, which I asked in the last video. I actually have a few more closing remarks, but they're not going to fit into this video, so I will make another, and I will see you there.